Hello, this is Year 12 Maths, further maths rather, and it's about the binomial distribution, which we do see in A-level maths, but in A-level further maths we take a bit further. For instance, we're meant to find the mean and the variance of a binomial distribution, and that's the main focus of today's lesson. So let's show you what I mean. Before we go any further, let's have a start to remind you what we did in A-level maths. A coin is biased, so its probability it will show heads, it says, on any throw is 2/3. Now this is a binomial situation because essentially there's only two outcomes. It's either heads or it's tails, and we care about number of heads. How many times am I throwing it? The coin is thrown 10 times, so we write x is binomial 10, and the probability of getting a heads is 2/3. It's one of those dodgy coins. And it says find the probability that after these 10 goes, you've got exactly 4 heads. Well, our calculator is very good at this. You can use either the Casio Class Whiz or the Texas TI-84 Plus. And I'm going to use the Casio Class Whiz, but essentially it's the same trick on both. So I do menu 7. Binomial. Now this is on this one, on both of them it's a binomial PD. So I'm going to go to that. This is an exact one. And what's my x value is 4. My n value is 10. And my p is 2/3. And I get 0.0569. 3 significant figures is the usual thing to do. If I want probability x is less than 4, though, you just got to be a bit careful. There isn't a button for less than 4. I have to interpret that, and I know that means the same thing as less than or equal to 3. So when I do this now, I'm going to do menu 7. I press down to get to binomial CD, and it's got the same. It's still 4 and 10 for the x. Oh no, it's not 4 now, it's 3. N is 10 and P is still 2/3, that's right. And I could this time get 0.0197, I suppose is the best way of writing that. So those are my two answers. 197,569. Yeah, so they're right. So that's what we've done in the past, and you'll notice how relatively easy it is to, once you know what it's a binomial situation, to get your answers from the calculator. And most times you'll be able to use a calculator. Sometimes you have to use a formula. You should recall that this is the NCR, posh way of writing NCR. This is the way we write distribution. This is the formula, p to the x, 1 minus p to the n minus x. These formulas actually come to, this formula rather is actually in the formula book. So you can see that's from the A-level further maths formula book, written exactly as I've done. But you'll notice there's two others. It says the expectation. This is the posh word for the expectation, sometimes written mu, sometimes called the mean, or the expectation. So there's lots of ways of saying the same thing. It might say find e of x. It might say find mu, this funny Greek letter, which we now know is called, said mu. Expectation, NP is the formula. That's basically the formula. And the variance is NP 1 minus P, so it's similar, but it's got this additional bit. Reminder, please, that if sometimes they ask you for the standard deviation, you have to square root the variance. So you'd use this formula, and then you'd square root your answer. So hopefully you've copied a few of those down, but definitely this one, because these two are new. These are not done at A-level maths. This is the new part, if you like, for further maths. A couple of things. When is it appropriate to use the binomial distribution? So basically there are two conditions that I want you to know about. One is that probability of success is constant, and 2, the trials are independent. Now I say there are 2. Sometimes we write there that there's a third, and the third one might be that the trials are random. So I'm just going to write that in here. The trials are random. So it wouldn't surprise me if you also saw that. But these are certainly the main two, that the trials are independent and the probability of success is constant. Now the probability of success is constant is just one of those ideas that is actually very important, because the whole basis of the binomial distribution is that the probability stays the same. So for instance, if you're rolling a die, then presumably it is always a 6 that the chance of getting a 2 on your next throw. But if you're taking penalties, a goalkeeper who stood 12 yards away, every time you take a penalty, you might get better at taking penalties, he might get better at saving penalties, you might get tired. So there's a whole different, or a whole set of reasons why the probability of you scoring on each penalty may not be constant. It may change every time, I don't know. So just be aware of that. But anyway, so we've got our 2/3 conditions. So using those, is the binomial a good model for these? And if it is, work out the probability, I suppose. A coin is biased so that a tail is twice as likely as head. Find the probability in 6 tosses. Exactly 4 heads will be obtained. Well, let's first of all just try and work out tail is twice as likely as a head. So what would that be? They add up. Oh, I see. So a tail is 2/3, I suppose, and the head would be 1/3. That would fit that bill. They add up to a whole one as well. So x is binomial. You're either going to heads or tails, and the probability then that in 6 goes, you get exactly 4 heads or tails. So we're interested in the heads, and that's the 1/3 here. So 6, 1/3. And we want the probability that x equals 4. Now, first of all, I think it is a great example of when you can use the binomial distribution. It's definitely got a fixed probability. It's 1/3 every time. It's telling me I was just about to say it's a coin, a die, but it's a coin. This dodgy coin that I've got has got a fixed probability. 1/3 every time I toss this coin is a 1/3 chance that it's going to land on heads. So that's not in doubt. Every throw are the independent. So that basically means, does that what I get on the last throw affect my chances of getting a head next go? And I don't think it does. So I think this is just a straightforward one. It's a good model. So I want binomial PD, and I'm doing it. I want x is 4, n is 6, and it's 1/3 for the probability. And I get 0.082, I think it was. 0.0823. And I think it's a good model. That's my view anyway. The proportion of a particular variety of seeds that fail to germinate is known to be 10%. If a random sample of 20 seeds is made, all right, so x is binomial. 20 of them I'm doing. I know that the probability of them germinating is 10%, 0.1. What's the probability that 2 or more fail, which is greater than or equal to 2? Which presumably, if I was going to do it, 1 minus the probability x is less than or equal to 1. Now, is it a good model? This one I decided was a good model. Is it? It's the proportion. Now, it's a bit dodgy. Is it a constant probability? If you assume it's a constant probability, and you assume they're independent, it's reasonably good. I would suggest reasonably good model. If you assume that those two things are true, whether or not they're reasonable is another story. But I'm just going to do it now anyway. So I'm going to go menu 7. I go to binomial CD, and I'm doing this thing. So I want a 1 for x, and n is 20.1, and of course it's 1 minus this answer, and I get 0.39, so presumably this is 0.608. 608. Well, I'll have a look in a bit if I agree with that. Number 3, 20% of the students travelling to college by bus. If 15 students are chosen at random, what's the probability that fewer than 3 travel on bus? Now, this is probably not a good model. And the reason I would suggest it's not a good model is the fact that they are probably not independent events. my gut feeling is these are probably, some of these people are friends, so if one person's late, it might make the other person late. Therefore, they're not independent events. So let's see what I put as my answers. Binomial is a good model, and I got the same answer in terms of probability. Independence may be an issue, but binomial, okay, yeah, so that's just agreeing with my reasonably good model. There might be a bit of an issue, but very often in maths you're not ever really sure in these statistics questions, but sometimes you go, yeah, it seems alright. The last one I didn't think was right though, so what did I put? Not a good model, as students on the bus are unlikely to be travelling independently, or at least not all of them. So yeah, we've got those right. Next example then, find the mean, variance and standard deviation of this. Alright, well first of all, we had our formula, didn't we? We knew that the mean was NP. So in this case it's 14 times by 0.24. Now this is the main part, I suppose, of what we're doing different in this at further maths than what we did in A-level maths. So there's not really much to this additional bit. It's quite nice that you get questions on this, to be honest. 3.36 I reckon. And the variance, well, I'm just going to write var equals NP 1 minus P. So that's essentially 14 times by 0.24, which I already know is 3.36, times by 1 minus P, and if I just quick calculation in my head, 0.76. So times up by 0.76, I reckon I get 2.5 and a bit, 2.5536. And the last thing is the standard deviation, and you should remember you square root your variance, 2.5536 square rooted, so I'm just going to square root my answer. And I get 1.59, well, 1.60 I suppose, to 3 significant figures. Then that's right, that's what we've got. Backward questions. So we've got a random variable x has a mean of 10.5. Now straight away, as soon as it says a mean of 10.5, I'm thinking to myself np equals 10.5. And a variance of 3.15. Well, that's np 1 minus p is 3.15. So I've set up two simultaneous equations, but the great thing about this is the fact that it says np and then it says np down here. So I can replace the 10.5 into this np. And effectively it gives me 10.5 lots of 1 minus p equals 3.15. I can divide 1 minus p, therefore is 3.15 divided by that 10.5. So let's just write that down properly. Over the 10.5. And when I've done that, my calculator, I've got 1 minus p equal to 0.3, and therefore p equals 0.7. And once I know that p is 0.7, I can go, well, n times by 0.7 equals 10.5, and therefore n is 10.5 divided by the 0.7, and I get 15. So I've got everything I needed. Hence find the probability that x is greater than or equal to 12. Well, this is now just a binomial question, I suppose, but again, you just need to be a bit careful. Greater than or equal to 12 is the opposite of less than or equal to 11. So if I just set this up, menu 7, binomial CD, number 1, x is 11, n was, I worked out to be 15, and p I worked out to be 0.7. So I get 1 minus 0.703, which sounds like 0.297. 0.297. Now, we're more or less out of time, and I think there's a couple of questions to go. Perhaps have a look at these. This first one says find the mean and variance of these random variables. And I'm going to pause and then put up the answers to you. So have a go at these. Yeah, this one's a backward question, but these are straightforward, find the mean and variance. You should be able to do those, given what we've just seen. Look, I'm going to ping up the answers in a bit, so I do hope you've had a go at these. You've got these, question 1, just find the mean and the variance. Question 2, this backward question. And these are my answers. So question 1, we've got 3 sets of answers for the mean and the variance. Question 2, that's the harder one. According to me, that's the answer. Make sure you can get those. Because in lesson, that's what we're doing. Exercise 2D, pages 30 to 31 is quite nice. It's very similar to normal maths, but just this little bit of an extension. Okay, thank you.